I'll upload the slides later on Teams if you need it. Yeah, so the pitching moment of the wing. Pitching moment is essentially the torque that is acting on the airfoil, considering any reference point as the point that you're calculating it about, and also considering that the lift force is going to be acting at the center of pressure exactly. So that is the assumption we're making here. And as I said, it is basically equivalent because we're taking the average. Yeah, so this is a center of pressure, and you can take any reference point to calculate the moment. The moment will just be equal to the distance between the reference point and the arm multiplied by the lift force acting on the center of pressure. So that is the formula here. Moment is equal to lift times arm. Yeah, so one thing is that we can see here also, as you increase the angle of attack of the airfoil, there is a tendency for the center of pressure to move closer and closer to the leading edge. See here, you can see the center of pressure is here, and in the next figure, the angle of attack increases and the center of pressure moves closer to the leading edge. And we also know that as the angle of attack increases, the total lift force also increases. So the two changes that are happening is the center of pressure shifts closer to the leading edge. That means if you're taking a reference point that is on the left side of a typical center of pressure, that would mean that your arm length is decreasing because your center of pressure is moving closer and your lift force will be increasing. So the product is lift times arm. So one quantity is decreasing, one quantity is increasing. So what we can theorize is that there is some reference point if we take the moment about that reference point, this increase in lift and this decrease in arm length basically cancel each other out. So that is called as the such a point exists is what we can find. Like early aerospace engineers have proved this experimentally and also like theoretically. So this point is called as the aerodynamic center. That is the point about which the pitching moment of the wing is independent of the angle of attack. And experimentally, we have found that this aerodynamic center, this point is the aerodynamic center in this case. Experimentally, we have found that the aerodynamic center will always lie, not always, it will always lie in like the neighborhood of 25% of the chord length. So that is it will be close to the point that is 0.25 times the net chord length distance away from the leading edge. So that is an approximate, a rule of thumb basically. It will be somewhere around that point that you'll find a point, find the aerodynamic center such that the pitching moment of the wing will be a constant with respect to angle of attack. Yeah, so this is called the aerodynamic center or AC. And this will be our reference point. Generally, if you're mentioning pitching moment, you can just assume that it will be about the aerodynamic center. So it is important to remember that pitching moment about the aerodynamic center is almost constant to the angle of attack. And this constancy is only maintained for relatively low speed airfoils. And also it is only maintained for some angle of attack ranges. If you go, for example, here in the situation, they mentioned that it is only between 0 and 12 degrees. So if you go like far beyond the specified angle of attack length, what happens is that the airflow basically stalls. And at the stall point, lift decreases drastically. So this like increasing and decreasing effects can't cancel each other out because lift will then decrease drastically at stall. That is why we specify it over certain angles of attack as well. We'll see this if we have time with XFLR5. So that is about the pitching moment. Now we'll go with the coefficient of moment. The coefficient of moment is also like it's similarly just a dimensionless quantity that is dimensionless, that is making the moment a dimensionless quantity. So that is you can compare it with another airfoil. So it's defined almost similarly to the previous coefficients of lift and drag. So coefficient of moment will just be your moment m divided by your dynamic pressure q times your area of your surface area of your wing times the chord length c. The chord length c is included also to make the coefficient dimensionless because moment has the dimension of force times length. And we know q times area also has the dimension of force times length, as we did earlier. This chord c is added to dimension to make the like force times length canceled out. So that is basically what c is there for. And also this is for the full wing. This equation is for the full wing because moment we're defining here, not moment per unit span or area or anything. Uh, um, this is what I was talking about, the mean aerodynamic chord earlier. Here, C is not just the chord length. If you have a non-rectangular wing, something like this, where the chord changes over the span of the wing, then essentially the C will be replaced by MAC, mean aerodynamic chord. That is essentially just the average of all these chord lengths over some integral. So yeah, this is about the coefficient of moment. Thing to know is that there is a sign convention for moment. If the moment is negative, that means that the moment is trying to turn the nose of the airplane down. If the moment is positive, that means that the moment is trying to turn the nose of the plane up. So we will always prefer to have a more negative moment because say you're close to the stalling angle. You're flying at some 10 degrees angle of attack, and you're close to being stalled. And in that moment, like if you're trying to, if you've got a positive moment, that means that even without any of your interference, the plane will basically try to turn itself nose up. And if it turns any more nose up, it'll just reach the stall line. So we will prefer to have the negative moment because it'll bring us away from stall without additional, um, uh, additional help from the elevators. So that is about moment and coefficient of moment. For the airfoil as well, there is a separate definition of coefficient of moment. It's basically just similar to how we did it for lift and drag. It's just made like lift per unit span. So similarly, it's be moment per unit span or moment per unit area, something like that. So it's also a sectional. There's also a sectional moment coefficient that exists, and this is what we'll be calculating. For the XFLR airfoil analysis section, for the wing analysis section, we'll be calculating the moment that I've mentioned, coefficient of moment that I've mentioned here for the full wing. Yeah, a few more things here. Coefficient of pressure next. The coefficient of pressure is basically just the, you can just think of it as the pressure at a point. So the equation is just pressure at a point minus pressure at infinity, essentially. P minus P naught. P naught is basically pressure at some infinity in the air distribution. We do this because if you're considering an airfoil, the airfoil will affect the air pressure around it. So if you're considering at any point around the airfoil, that won't give you like an accurate characterization of the airflow itself. So we take a point at infinity, which is far removed from the influence of the airfoil. That is P naught basically. It's the free stream pressure. Similar to how we define free stream velocity, because the airfoil affects the velocity of the air around it. So that is P naught here. It's basically P infinity. So you can just think of it as surrounding pressure. P is the pressure at the given point minus P infinity divided by Q, the dynamic pressure. Q is just a scaling factor. It doesn't really, it's okay. You can consider it as just the difference between the pressure to the surrounding pressure. So if Cp is positive, that means that your P minus P naught is positive, which means your P is greater than your surrounding pressure. If Cp is negative, it means that the same thing, the opposite thing. That is P minus P naught is negative, which means that P is less than P naught. So the pressure there is less than the surrounding pressure. We'll see this. The convention is useful later. Yeah, so next, I think you've done this also a little bit in session one, but I'll just quickly go over it. The Reynolds number is basically defined as rho VL by mu. Rho is the density of the air, V is the velocity of your airflow. Length is any characteristic length for wings and what do you call for wings and airfoils. We'll always take L as the chord length of the airfoil. L will not span length. I think I made a mistake here. L will just be the chord length of wings and airfoil. So that is important because we'll see in XFLR5 how we can change the chord length and get different Reynolds numbers that we want. One more thing here is that rho by mu, or rather mu by rho, is defined as one singular quantity, which is called which is marked by small v. That is the small v here. It is called as kinematic viscosity. Uh, if I didn't mention the terms earlier, rho is density, v is velocity, L is characteristic length, and mu is the normal viscosity of the fluid. Here, mu by rho is basically the viscosity upon density. This is what we call as kinematic viscosity. It is a term that is basically characteristic of the viscosity of a moving fluid. Reynolds number itself you can think of as the characterization of the viscosity of the fluid. It is basically a ratio of the inertial force to your viscous force. So basically, a higher Reynolds number means your airflow is having a very low like viscosity and viscous effects. So that means your friction effects will be reduced. Is basically what that means. That is what I want. Inertial upon viscous force is basically Reynolds number. Reynolds number is also used to determine basically the type of airflow that is going on. If it is greater than 3000, that means you're having a turbulent flow, and less than 2000 implies laminar flow. Laminar flow is essentially where you just got like streamlines that are basically not crossing each other and they're not interfering with each other. But most of the cases we'll analyze will be having turbulent flow above 3000. So yeah, you can just think of it as basically like a measure of the viscosity of the fluid. Next up is your assignments and stuff. We'll go over that towards the end. So let's start with the actual XFLR5 section. So again, just to recap, we've gone over the lift coefficient, drag coefficient, moment coefficient, and pressure coefficient. We'll basically be plotting these versus angle of attack with our XFLR5 analysis. So yeah, that's it about that. These quantities are important. If you've got any doubts or anything about this, you can ask in chat or you can raise your hand and I think Nitin will unmute you. You can ask. The point where it stalls is just after the critical angle of attack. You've seen the graph, I think, in session 1. I'll show you the graph again when we're doing XFLR5. Is there like significant lag for the video or you're able to follow?
Like I was watching, there isn't that much lag, but like if anyone is unable to follow, you can send it in the chat and we'll try to fix it.
Okay, fine. Sure. So no other doubts? All right, so let's start with XFLR5. Yeah, so a couple of things. When you start up XFLR5, you'll be just greeted with a blank screen. So there's a couple of things that you have to do. Just go to File and open a new project. Go to Module, go to Direct File Design. That's what we'll do first. Yeah. By default, I think it defaults to dark mode. If you want light mode, you can just go to Options, Preferences, Display Options, and set it here. I've set it to light. Yeah. Also, before getting started, I think some of the default settings might be like messed up for a few people because I reset my settings and it was giving me a couple of errors. So just follow these steps before we actually get started. You should go to Direct Analysis. Under Analysis, Advanced Settings. And you should set your iteration limit to 100. Sometimes it's set to a 0, I think, which will just give you an error. So you should set this to 100. Also, under Module, go to Wing and Plane Design, Analysis, Advanced Settings. Max iterations here also it was set to 0 for me, so you should be setting this to 100. Otherwise, like it won't give you any results. One last thing, under View, you'll have 3D scales. I think some issues there, but 3D scales should pull up this window where you have your lift, drag, and your velocity, like vector scales. So make sure to set those to 0.1 because it was set to 0 for me, and some issues were there with that. So just that, and that's it. That's all you have to do before starting. Um, okay, yeah. So that is all the settings dealt with. So once you agree to that blank screen, just go into module, start up direct file design. So this is the screen where we'll be loading up our airfoil. Airfoils are basically the type of airfoils that XFLR5 can recognize will be stored in the .dat format. So the way that you can download it is basically just you can go on Chrome or any browser. You can look for just search up airfoil.file. This one UIUC airfoil dataset. And yeah, this is a pretty like comprehensive database which has a lot of like commonly tested and you know uh, tried and true airfoils basically. It's characterized alphabetically, so you can just go down here, go down to the A to Z directory, and if you know the name of the airfoil that you want to use, you can just use the alphabetization. Whatever airfoil that you want to use, you can just right-click the dat file and just click Save Link As, and you should just be able to save it as a dat file here. So once you save, you can just save it to any folder. And once you've done that, you can go into XFLR5, go to open here on the top left, and you should be able to open that dat file and load in the air file. So this is the air file that I've just downloaded. It's called the AG12, I think. But we'll be using a different air file for today. I was just demonstrating how you can load up a dat file into the program. Yeah, we'll be using the Clark YF file because this is what we'll be using for your assignment as well. So this is your air file.
Ishan, 1 second.
Uh, yeah.
One in chat wants you to repeat the process. Uh, Bhavesh, if you can tell what process you want to repeat in the chat. Yeah.
I think he wants me to like show how to load the air file again. I'll just show that. You can just look up airfoil.file, and this link should pop up, UIUC airfoil dataset. Go down to the A to Z directory. You can click on the GIFs here to actually see what the files would look like. And once you've decided which one you want, you can just right click on it, save link as, and you can just store it as a dat file, DAT file. Just press save, and then you should be able to open it in XFLR file. Another way to do this is you can just left click on it, and you'll be loaded into this HTML file basically. You can just copy this entire thing into a text file and just give it the .dat extension. It's the same thing. This is how this is called the selig data format, by the way. This SELIG selig. The selig data format is what is like I've seen is best for loading into XFLR5. So you can look for that. But this directory is already like entirely selig, I think. So that's fine. To actually open it in XFLR5, you can just go to the top left, open, and you can load up your dat file here. Choose whatever and just click open. So I've already loaded in my Clark YR file. So most of these airfoils that are given in this database are already like tested and true. Like you've already got all the graphs and the data that you need to actually make it work already because people have run wind tunnel tests with most of these airfoils. So that is why it is best to like use a pre-existing file. Otherwise, there is also the option to make your own file. Just click show here under spline file. And you should be able to just drag around whatever you want, make your very own airfoil. And you can store it with like this button at the top here, store splines as file. And you can just click OK. So now this weird shape thing is also like you can load into XFLR5. But I wouldn't really suggest this because these are already like pre-tested air files that we are downloading. So preferably you should get one of those. So I'll just delete the spline from it.
Sure.
Yeah,
Can you go to the chat 1 second? A few of the people have it.
database side. We will be uploading the video, like the recorded session on YouTube, so you can just go back and watch that because I don't really expect you to follow the like exact steps right now because I can't really like go step by step and also like wait for each step. That's why. So it is better if you're like just taking an hour after the class and going through the session and like following the steps along there. So I'll just show you the basics and the theory and stuff here. So we will be uploading the recorded session. So yeah,
Also, the website,
um,
the database link, and it.
yeah, I'll just send that if you want. But you can just look up airfoil dat file and you should be able to find it. I'll also upload this in the resources section. Yeah, this is what I was talking about. Some of these like files in the website are stored in the like in a different format than XFLR5 like recognizes typically. So you'll have to go looking for the Selig file. The ClarkWire file on the UIUC site is not exactly like good for loading into XFLR5. So you should be going looking for the Selig file format. So you can just look up, so say ClarkWire airfoil, select that file. Um, this is the one we want, a ClarkWire airfoil. This is another site that is useful. Just send this as well. This happens when your file is not fit for being loaded. So you can just go here, go under select format that file. This is the file that I have loaded in. You can just right click the select format that file here and save this one. If you do want to follow along, just go to save as all files and give it a .dat extension. You should make sure to make it all files, otherwise it will just be a text file. So this one should work. This is a select format file. This should work for you. If you're getting something similar to this, make sure to just do what I did. Just look up the select format that file. Okay, yeah. Someone also asked to, I think, repeat the settings stuff. You can watch the video, but I'll just, for this one, I'll just repeat the settings real quick as well. You can just go to audio, direct analysis, option analysis, X file advanced settings. Make sure to set the iteration limit to 100. Also go under wing and plane design, analysis, advanced settings, maximum iterations here as well to 100. One more thing is under view, 3D scales. Um, there should be a toolbar that pops up for you. I'm not sure why it's not showing up for me now. But under 3D scales, you should set your vector scales for your lift, drag, and your velocity to 0.1 or 1 or something, because that will be the way that you visualize your what do you call your plane analysis. So we'll see that. You don't have to worry about it now if it doesn't show up for you as well. I'm not sure why it's not showing up, but it's okay. We'll start with airfoil first. So again, I'm just loading up the ClarkWire airfoil. You can set the color and stuff of your airfoil if you want here, but it's not visible. So you can mark here show to actually hide and show the airfoil, and center line, which will show you the camber line. This is the camber line of the airfoil. Um, so before actually starting the analysis as well, we should go under foil, refine globally, and there will be this what do you call column called the number of panels. The number of panels is basically like a panel is basically a point that you're using to characterize your airfoil. We see these like dotted points. That is a panel basically. As you increase the number of your panels, the like accuracy of your analysis increases, but also what happens is your processing time increases drastically. So preferably like 100 points is what like typically we'll be using. It'll be like kind of the sweet spot between efficiency and accurate analysis. So you should change the number of panels to 100, and you can just overwrite your existing airfoil. So that'll be showing up under points here, 100 points now. So it should be a bit faster for us to analyze. Yeah, so some terms about the airfoil. This is a thickness percentage. So the thickness percentage is basically the maximum thickness, the maximum distance between the upper and the lower surface of the airfoil. What this is telling us is that the maximum distance between the upper and lower surface is 11.7% of the chord length. The chord length here is 1. Most of the airfoil files that you download will already be normalized to make the chord length 1. What XFLR5 does is that it takes this normalized foil, it analyzes this, and then scales it accordingly when you're using different chord lengths, is what happens. So automatically it should be normalized, but I'm just stating that you should see this at 1. The trailing edge should be at 1. Yeah, so the thickness percentage is basically stating that the maximum thickness of this airfoil is 11.7% of the chord length. That is 0.117 units here. And this at basically states that this maximum thickness occurs at 27% of the chord length. So if you consider the chord line, that is this x-axis here, if you consider the chord line, then this maximum thickness of the airfoil is occurring at 27% of this one, that is at 0.27 approximately. If you zoom in, you can zoom in with your scroll wheel, by the way. It should be around here where the maximum thickness occurs, 0.27 almost. That is what this is telling us, thickness and at. Next thing is our camber. Camber is basically 3.43% is written. That means that basically like the maximum distance between the center line or the camber line and the chord line is 3.43% of your chord length. That is 3.43% of 1 here, or 0.03 units. And this maximum distance between camber line and chord line is occurring at 42% of the chord. At is at 42% of the chord. That is at 0.42 here because our chord length is 1. So around 0.42, we see that the maximum distance between the camber line and the chord line is here. And this length will be 0.03 because camber is 3.43%. So yeah, that is mainly most of the things you should know before starting. So this is how you load in your airfoil. Next, we will be going on to the analysis of this said airfoil. For this, you can go into your module section, Xfoil Direct Analysis. Like I said, XFLR5 is basically just a graphical interface for the command line tool that is Xfoil. So that is why it's mentioning Xfoil here. So yeah, you can go into direct analysis. Yeah, also make sure to select direct analysis and not inverse design because that is different. Yeah, so let's start. You might be having some different quantities on your X and Y axis here. So I'm having CL by CD versus alpha. You might be having something different. How you can change that is you can just double left click on your graph, and you should be able to see like the quantities that you should be able to define on the X and Y axis. So here I've given CL by CD on the Y axis and alpha on the X axis. You can select whatever you want here and just hit OK. You can also change the scales manually here if you'd like, but typically it just defaults automatically to the right scale. So just press OK, you'll get the CL by CD versus alpha graph. Again, these quantities are for the airfoil. So this is the section lift coefficient, not the actual wing lift coefficient that I mentioned earlier. This is the section lift coefficient CL. CD is the section drag coefficient. Alpha is the angle of attack. If I didn't mention what the angle of attack is, the angle of attack is basically just the angle that is formed between the relative wind direction and the chord line of the airfoil. So if I'm angling my airfoil up, that means the chord line and the relative wind will make an angle. That is called alpha or angle of attack. So yeah, that is alpha here, and that'll be what is on most of our x-axis anyway. So we have a CL versus alpha, CM versus alpha, that is moment, coefficient of moment, and CD versus alpha here. So the way that we start an analysis is you go under analysis, define an analysis. So then this window should pop up. This has a couple of analysis types here. Type 1 essentially means that it is a fixed speed analysis. That is, you're assuming a fixed speed aircraft and you're changing the other quantities to change your CL and CD. That is basically you're changing your alpha to change your CL and CD. So that is the type 1 analysis. You're keeping a fixed speed and you're running the analysis. Here we have the option to specify our Reynolds number. So here what I have given is a Reynolds number typically for small aircrafts is like around 2 million. So 1 million should be a good place to start. Like far lower Reynolds numbers, it might give you some like janky graphs. So you should probably start with 1 million or 2 million or 500,000. But we will be running a batch analysis later with a bunch of different Reynolds numbers. But for a basic analysis, 1 million is a good place to start. This is just 10 raised to 6. Mach number is basically the ratio of your it is a ratio of the speed of your aircraft to the speed of sound. So here where I'm planning to analyze like a fixed speed that is like far below the speed of sound. That is why by default Mach number will be set to 0. And most cases you can just leave it as it is. Like most of our like requirements, you probably won't need supersonic flight. So that is why this is typically left as 0. It's not exactly like it doesn't mean that the velocity is 0. It just means that you don't expect it to have any like supersonic effects because it is so like because the velocity of your aircraft is so far less as compared to your speed of sound. That is why it is set to 0. These quantities you can leave as it is. This just means like the transition from the laminar to the turbulent flow is happening, I believe, at this Reynolds number. But you don't really need to worry about these. The default values should work fine. And the density and all this as well, you don't really need to worry about. Also notice here the small v quantity. This is the kinematic viscosity I was talking about earlier. So the kinematic viscosity is basically just viscosity by rho density. So you don't. It will be used for the later types of analysis, but mainly we'll be dealing with the fixed speed analysis for the session. There's also like type 2, type 3, type 4. You can see the quantities that you're keeping constant here. The quantities that you specify here will be kept constant and everything else will be variable basically. Another interesting one is type 4 analysis. This is where you specify a particular angle of attack and change the Reynolds numbers to change your CL and CD. Here, we don't really need to worry about it right now, but it's interesting to see the trends sometimes. So we'll start with the fixed speed analysis. Make sure to set the number to something close to like in the millions range. So you can just click OK here. So this tab on the left side is basically your analysis here. Currently, we've just defined the constants for this. So now we have to actually run the analysis for some sequence. So that is on the right side here. This is alpha basically. This is your angle of attack, the first one. If you want to vary your angle of attack and notice your, and check the trends for your other quantities, this one will be what you will do. If you want to change your coefficient of lift over some sequence, this is what you should do. But we will be doing the angle of attack analysis. So that is the, make sure to tick this one. Tick sequence, and this will be your starting angle, and this will be your ending angle. I've decided to run it from -5 degrees to 30 degrees. If your angle of attack is negative, what that means is that your airfoil is facing downwards, basically. And if it is positive, I'm sure as you've seen before, like it's just the airfoil pointing upwards. So we are basically running all these different angles. This delta is your increment value. So that is your analysis will be for -5, -4.5, -4, etc. up to 30 degrees is what this means. I'm setting my increment to 0.5. So make sure to take these as well and analyze. Now, once you've clicked analyze here, this window should pop up. Um, so yeah, some points you might get this, you'll get the converged after some n iterations message here. If some points may go unconverged. Unconverged means like the software is not exactly perfect, and like some situations might be too complex for it to analyze, or some errors might have come up there. That's what unconverged means. Basically, the software just keeps looping until the error of the analysis becomes minimum. Unconverged means the error diverges and the error doesn't become zero essentially. So just if as long as your the majority of your points have converged, you don't really have to worry about it. Some points have unconverged, gone unconverged here. It's okay because it's just like one or two angles in between. That means the program wasn't able to determine the values there. So you can close that. Yeah. So your graphs might look a bit weird now. So you should right click your graph and just like reset all the graph scales. This is better to see. This is what I said about the scales like automatically fixing themselves. So yeah, these are the graphs that are basically going to let us analyze the airfoil. Um, so let's start with the CL graphs. You can use your number keys to alternate between the graphs 1, 2, 3, 4, 5, and press A again, the A key, to go back to the all view. So let's start with the CL graph, CL versus alpha. So this has got the lift coefficient on the y-axis and the angle of attack on the x-axis. So what we can see is that as the angle of attack increases, lift coefficient increases linearly up until a critical angle. So this critical angle we see here, if you zoom in close enough, you can see it's around 14 degrees. If you increase the angle of attack of the airfoil any further beyond 14 degrees, you'll start to get stall and those issues and stuff. So ideally, we always want to operate below this range. And once you start stalling, you lose lift and you'll start to nosedive basically. So this is a situation always to avoid. What is to the right of the critical angle. So the linear increase of CL with alpha, you can think of it like as you increase the angle of attack, what happens is that your airfoil essentially mirrors like an airfoil of higher camber. And we know that a higher camber airfoil produces a higher lift at a particular angle of attack. What you can see, think of it is that, so say, look at this. Your center line essentially, if you were to increase your angle of attack, your center line essentially goes higher and higher. So it kind of simulates the effect of having a higher camber airfoil. So that is why the lift coefficient is kind of increasing with the angle of attack. The stall is happening because at some point, the what do you call the airflow basically gets detached from the airfoil. In most other cases, in stable operating conditions, your airflow will be staying stuck to your airfoil. But at stall, what happens is that the flow separates off and it forms some turbulent vortices. So at that point, you'll start to lose lift because the way that the airfoil generates lift is essentially by what do you call changing the direction of the air entirely. So if you've got some air coming in along the x-axis direction, ultimately when it leaves the airfoil, it'll be getting some downward velocity component as well. That momentum that is imparted by the wing to the air is essentially like the reaction force of that is basically what is generating the lift of the air. So if the flow gets separated, that means that there is no more any deflection of the air as before, and the air doesn't really get the downward component, and the lift starts to drop drastically. That's basically what we're seeing after the stall angle here. So that is mainly it about the CL versus alpha graph. So this is a pretty important graph. From this, you can calculate the CL at any point, and using the lift equation that we saw earlier, we can use it to calculate like how much weight a possible like aircraft can support at a particular angle and a particular velocity. So this is a very important curve. Next, let's do the CL by CD versus, or let's do the CD versus alpha graph. So CD versus alpha graph, what you can notice is that the CD stays almost constant even for a particular range of angles, and then kind of drastically starts increasing. What you can think of it is like this basically. So as you increase your angle of attack, the what do you say? The surface area of the airfoil that comes in direct contact with the relative wind basically increases. So if you go here, this is a polar view, that is our graphs, and this is the CP view basically, the left side. You can click here to actually see the airfoil and its CP distribution. So this graph we'll talk about later, but for now, just you can notice the airfoil. As you go to, you can click on the what do you call the angles on the left side here to actually see the higher operating points of the airfoil. So if you go to a super high angle, what you can see is that the relative wind is basically this dotted line direction. And what happens is you increase the angle of attack is that the amount of the surface area that is like directly coming in contact with this air is increasing. So essentially, your airfoil is starting to mirror and look more and more like basically a flat plate. And the flat plate is basically like the highest amount of drag that you can get. It's super like it's not very aerodynamic. So what happens is this amount of the surface area is increasing, and that is why this drag is increasing with your alpha. So it kind of starts to look more and more like a flat plate. That is why this drag is increasing. The exponential increase sort of happens near the stall point, if you can notice. Stall point we said was around 14 degrees, and the exponential increase is also around 14 degrees. This is because if you didn't see it, is still 14 degrees, and that is where like the kind of rise starts. This is because like the flow separation also causes like loss of lift, and it also causes drastic increase of drag. That is why this exponential increase is shown. But you can also think of it like the what do you call it? It resembles a flat plate more. That is another explanation for this. So that is mainly it about the CD versus alpha graph. Ideally, you want it to like stall and also increase the drag at a higher angle because you want to operate it at a higher angle of attack. But mostly, like practically, airfoils typically have like a 15 degrees or less as a stall angle and as the drag angle, drag increasing angle. So we should always try to stay below this angle. Yeah, so that is CL, CD. And let's talk about the CL by CD graph. CL by CD is essentially a measure of the efficiency of flight. So ideally, you want a high CL and a low CD, so a high amount of lift for a as low as possible amount of drag for a particular angle of attack. So this is essentially maximizing lift and minimizing drag. So this is the efficiency. You can say basically the efficiency curve of the airfoil. If CL by CD is maximum, that means the flight is most efficient. It's generating the most lift at the least drag possible. Here for this graph, we can see that the kind of peak of the CL by CD curve is basically around, if you zoom in, uh, around 3 degrees to 7 degrees is the peak of efficiency of this airfoil. But as we have seen, CL basically increases all the way up to 14 degrees. This doesn't mean that like if the peak of the CL by CD is here, that doesn't mean that the highest possible lift you can generate is close to this angle. It just means that the most efficient flight is at 3 to 7 degrees. Still, like you can see that at 14 degrees here, the CL by CD is extremely low. That means it's not very efficient flight. It's extremely low compared to here. But still, that is the point, which is generating the most amount of lift. So those are kind of independent of each other. This is more like an efficiency curve. So ideally, you want it to have a large region of high efficiency or a large peak, basically. Yeah. Um, yeah. And then about the moment graph. This is the CM versus alpha graph, coefficient of moment versus alpha graph. One problem with this is that I mentioned that typically when we mention moment, we are talking about the moment about the aerodynamic center itself. But what XFLR5 does is that it looks for the center of gravity that you have defined, and it will calculate the moment about the center of gravity. But the problem with that is that the airfoil, so far, if you have noticed, we haven't really defined any center of gravity, and you can't define a center of gravity for the airfoil analysis part. So what XFLR5 defaults to is it calculates the moment about the leading edge point. Basically, it calculates a moment about this point, the leading edge. And that is why it is not really following the expectation that we had. The expectation that we had was that moment would stay constant with alpha because we are measuring moment about the aerodynamic center. But we do see that it is not the case. There is some fluctuations in the moment. We'll see to this later. There is a way to ensure that we get a CM versus alpha graph that is almost constant. So mainly this is not that important as of now because there's so much fluctuation that it is kind of hard to explain it each part anyway. So we'll wait for the aerodynamics. We'll wait till we can specify the center of gravity of the airfoil or the plane rather to actually what do you call get the CM versus alpha graph as almost a constant. One more thing, you can see the what do you call the signs here, the signs that we mentioned earlier. The positive CM means that essentially it's trying to turn the nose upwards. Negative CM means it's trying to turn the nose downwards. So here we see that most of the entire graph is below the x-axis. That is, the entire graph is having negative moment. This means that at any point, the what do you call the airfoil is basically trying to turn the nose downwards if you're considering the center of gravity at the leading edge. So it's trying to turn the airfoil downwards, and that is a very stable flight because it will help us avoid stall. As soon as we get close to stall, if you just let go of the elevators, it will automatically come down to a what do you call stable angle, is what this is telling us. So it's always preferable to have negative CM. A higher negative CM means it's a higher moment, based, yeah, in the nose down direction. So yeah, that's almost all the graphs. There is this CL by CD graph as well, which is not as important. I think I haven't really seen too much about this, but we can just quickly go over this as well. Um, if you have noticed, it's like this sharp increase here essentially is stating that, yeah, if you zoom in enough, you can see that this entire region is almost lying in the neighborhood of like CD equals 0.01. So there's such a huge like range of CL for the neighborhood that is close to CL. CD equals to 0.01. The reason for this, you can kind of look at the other graphs. So what you can see is CD equals 0.01 in the CD versus alpha curve, this one. You can see that CD equals 0.01 is basically like the, this is CD equals 0.01, this point. And this 0.01 is basically maintained for a large range of angle of attack. It's going almost from like -5 degrees to +7 degrees. It's close to 0.01. So yeah, so essentially what that means is that at this 0.01, you have such a huge range of angles of attack to work with, -5 to some 7 degrees. And if you look at the CL graph, what you can see is that from -5 to 7 degrees almost, like that is almost this entire range. And you can see that over that range, CL varies over such a large distance, like around like -0.2 to 1 or so at 7 degrees. So that is why there's such a large range of CLs for the particular CD of 0.01. So that is this sharp rise that we see. If you see, it is from -0.2 almost to 1, 1.2, the CL goes. And this decline here is basically afterwards. So this also you can explain by looking at the other graphs. Here essentially for a range of CL for like from 1.5, I believe, from 1.5 to like 1.2, you're getting such a large range of CDs. That is also basically for a CL range from 1.5 to 1.2, that basically means like this whole region, the stall region. From 1.5 to 1.2, you're operating over a like an angle of attack range of almost like 7 degrees to 25 degrees or so. And from 7 degrees to 25 degrees, you'll have this exponential increase of CD. That is just like around 7 degrees to around 25 degrees. You'll have such a large range of CD. It is going from almost like 0.01 to 0.3 or so. And that is what you are seeing here. Over this small range of CL, you're getting a large range of CD, 0.2 to 0.01 to almost zero point 0.3 or so. That is what we're seeing in this section. So it is just it's just a representation of the other graphs together. That's it. So this is mainly it about the airfoil analysis part. One last thing is that one more thing is that if you want to hide this graph for some reason, you can just go to the left side here and you see this cross here. You can just click the cross to hide and show these airfoils or these polars particularly. It will be useful for the next section. So yeah, one last thing about airfoils. I'll be deleting this curve for now. Yeah, so one more thing about airfoil analysis is you can go under analysis, go under batch analysis. And a batch analysis is essentially where you're doing the same analysis that we did earlier, but over a range of Reynolds numbers that you specify. So here I'll be doing the same analysis that I did earlier from a Reynolds number from 30,000 to 8 million. So you'll get a bunch of curves of the same type that we saw earlier. So the reason we're doing this is that next thing that we're getting into is going to be, what do you say? It'll be wing analysis. And for wing analysis, we'll be needing these different Reynolds numbers and different operating points. You should note that if you don't do this batch analysis before we go into the wing analysis, you'll be getting some errors like flight point is the point is out of a flight envelope and stuff like that. I've mentioned that in the PPT in case when you're doing the assignment, you get it. It looks like so essentially you will have to include whatever you're using in the Reynolds number that you're using for the wing analysis in the batch analysis for the airfoil itself. If you don't do that, you'll get some errors like the points are outside the flight envelope. So essentially what XFLR5 does is it takes these analysis that we're doing at these different Reynolds numbers. And when we're doing wing analysis later on, we'll be using the same data for performing that analysis. So we have to do this first, is what I'm saying. It is a requirement for wing analysis. So again, it's literally just it's just the same analysis that we did earlier for the airfoil, but repeated for so many different Reynolds numbers. All done together basically. Here as well, you can choose the polar type. T1 is type 1, fixed speed analysis. T2 is fixed lift analysis. And T3 is rubber core polar. This is not that important. I think we haven't really seen much of this. So yeah, we will again be doing the fixed speed polar because that is like mostly we'll be dealing with fixed speed analysis for the session. So T1, just select T1. Here we'll give our angle of attack range here directly. So this is the alpha one. Just take this one, not the CL, alpha, and give the starting angle and the ending angle and the increment. So I'll start at -5, end at 30 with an increment of 0.5. Make sure to take this from zero thing. It makes your analysis a bit more accurate, I think, because essentially you're taking your analysis from 0 to 30 degrees, and then you're taking from 0 to -5 degrees. It helps the software somehow. I'm not exactly sure, but it is better for the accuracy of the end results. You just take from 0. Make sure to store operating points. Tick this and tick this. From there, yeah, this is essentially the Reynolds numbers were changing. Mark number is still 0, like we said earlier. Encrate is 9 as before. You can keep these as default. Just in case you need some more Reynolds numbers, you can just click on actions here and click insert after. That means that after 60,000, it will give like any even interval and do the next Reynolds number analysis here. 70,000. If you want something between 100 and 130, you can just click insert after here. 115, or you can just left click on this and whatever Reynolds number you want to analyze, you can just input it there. So yeah, that's it about setting up the batch analysis. So just after you're done setting it up, just click analyze. Once it's done, you'll just get a message saying it is completed. You can just close this. Yeah, by default, if you're seeing your Reynolds number range will only be till like some 3 million or so. I have added some extra like Reynolds number ranges simply because like we'll be using a higher Reynolds number for your wings and stuff. If you're using it, if you're using the higher Reynolds number, then you can add till later. But if it is okay, that if the Reynolds number that you're using for your wing analysis is in the range of your batch analysis here, then you don't need to add anything else. The attendance, I think, has been released earlier. One more attendance form will be released towards like the end of the session. For GNU and Linux, I'm not really sure. I think there's a version of XFLR5. I'm not exactly sure. I'll have to look into it. I'll let you know later. We'll be having a doubt session towards the end, or like as the last session number 8. So I'll check it out and I'll let you know. But there should be some version of XFLR5 that runs. I'll see. So yeah, once you've finished with your batch analysis, you'll basically get like this a bunch of graphs. So this is where I said the hiding graphs comes in handy. So you can just click here to show all of the curves that you have. You can just click the top arrow here for the Clark airfoil to hide everything. Then you can just go on toggling whichever ones you want. So yeah, this is the 1 million analysis that we saw earlier. It'll be stated here. RE1 means 1 million, 0.875 means 0.875 million. So yeah, M is Mach number, N is your critical, what do you call, change from laminar to turbulent flow. So yeah, what we can see is if you're considering like relatively higher Reynolds numbers, I'll start from 200,000. So what you can see is that as you go to higher and higher Reynolds numbers, what is happening is that the efficiency curve shifts higher. That is, CL by CD becomes higher and the flight becomes more efficient. And another thing you can see is CL graph is almost exactly the same. But as you add more Reynolds numbers, you can see like a bit of a trend. After you've gone up from 1 million, you can see how adding the graphs for the CL versus alpha graph at least, as you increase the Reynolds number, you'll see that the stall angle shifts to a higher and higher value. So this point is essentially the Reynolds number equals 8 million curve. So here you can see that the stall angle shifts to around like 19 degrees as opposed to like, if I remember, 14 degrees that we had for the 1 million Reynolds number curve. For the lower angles, it's almost exactly the identical behavior that we had. It's just stall is shifted to a higher angle, and also CL max is shifted. The maximum value of CL increases as you increase the Reynolds number. Like I said, Reynolds number is pretty characteristic of airflow. It is kind of a measure of the viscosity of the air. So yeah, that is about the CL versus alpha graph. CM versus alpha you don't need to worry about right now because it's about like the leading edge and it's not about the aerodynamic center for now. Still, we can see it's almost like identical behavior with Reynolds number. CD, one interesting thing you can see is um, if you increase your Reynolds numbers, I'm just like subsequently toggling the higher Reynolds numbers basically, if you can't see. Um, so if you notice the CD versus alpha graph, as you toggle the higher and higher Reynolds numbers, you can see that the CD graph basically shifts lower and lower. So that is the drag decreases as you increase the Reynolds numbers. This is consistent because so the lowest one is your highest Reynolds number. So this is your 8 million Reynolds number. The higher ones will be your higher Reynolds numbers. This is consistent because, like I said, Reynolds number is just a measure of like the viscosity of the air. So if you have like a more viscous fluid where you're moving in, that means you have a higher amount of friction to generate more drag. So if you have a higher Reynolds number, that means you have lower viscosity, and basically you're generating less friction drag. So that is why your CD is getting lower and lower as you increase your Reynolds number. So that is it about this. This as well you don't really need to worry about. So yeah, once we've done with this analysis, we'll move on to wing analysis. So this will be like I think, most important section here. So if you guys have any doubts about this, you can ask in chat. No, CD includes both friction drag and pressure drag. Friction drag and viscous drag is basically the same thing. Friction is viscosity. So CD includes the drag generated due to pressure and also the drag generated due to friction or viscosity. I forgot to mention one thing. I said I would explain this curve, right? Cp versus x. So this is the coefficient of pressure versus the length of the airfoil that we saw. So basically, this is the pressure distribution of the airfoil. If, like I said, if Cp is negative, it means that the pressure of the surrounding, if Cp is negative, it means that the pressure is less than the surrounding pressure. If Cp is positive to the lower half, you can see Cp is positive. That means that the pressure is higher at that point than the surrounding pressure, is all that. So you can toggle through your angles of attack here. As you go from minus 4.5 or so, if you haven't noticed, one of these is the upper surface of the airfoil. One graph is exclusively for the upper surface, and another graph is exclusively for the lower surface of the airfoil. If you go to the right side here, you can toggle the pressure display, and this will show you like a cool imagery of basically it's just a visualization of this graph on the airfoil itself. I'll explain this 1 second. Let's start at 0 degrees. Or rather, let's start at a pretty high angle of attack because it's easier to see it here. So what you see is this higher graph here in this case is basically the upper surface of the airfoil. This means that for the upper surface of the airfoil at x equals 0.2, around like x equals 0.2, the CP value is around 0.7 is what this means. So what this says is basically the higher curve is basically the what do you call upper surface. The lower curve is basically the lower surface of your airfoil. And yeah, it is basically just the pressure distribution over the airfoil, like which part is generating the highest amount of lift and drag and whatnot. So this part is what contributes to the pressure drag, like I said. Drag has two components, viscous and pressure drag. Viscous drag is due to the friction of the air, and pressure drag is basically if you resolve these components along the direction that is, along the fluid flow, that is basically what you'll be getting as pressure drag. So yeah, this is the CP versus X graph. One is the upper curve, one is the lower surface curve. As you go higher and higher, there's like a bit of a skip here, I think between 7 and 15. That is why there's like a drastic change. Not sure why that's happening. It should be okay. I mean, because our graph came out fine, I think. This is a Reynolds number at 30,000, by the way. That might be why these have gone unconverged. Like I said, yeah. So this is just your CP curve. As you go higher and higher, you see just before the stall angle at least, your CP will be your CP for the highest upper surface will be increasing, and the CP for your lower surface will be increasing in the opposite direction. So this essentially means that the lower surface is having positive CP. Positive CP means that, like I said, the pressure of the point is higher than the surrounding pressure, and that means that basically, this is a high pressure region compared to the surroundings. What these arrows are representing is basically these arrows are also, if you haven't noticed, it's drawn perpendicular to the airfoil. And the direction of the arrows is basically showing if it is low pressure or high pressure. If the arrows are pointing away from the airfoil, that means that it is a low pressure region with respect to the surroundings. That means that the CP is negative. And if the arrows are pointing towards the airfoil, it means that it is a high pressure region and the pressure is higher than the surroundings. Also, this point that you see here, this point, that is the center of pressure. And the length of this arrow is basically representative of the lift. This point is the center of pressure. And like we saw earlier, if you shift the center of, what do you call it? If you shift the airfoil higher and higher, you can see how the center of pressure shifts to the leading edge, shifts towards the leading edge. So that is something cool you can visualize with this view as well. So yeah, it's basically just a pressure distribution curve. You can also click displacement thickness here. So this is basically the boundary conditions of the air. So the airflow here, say let's start at 0 degrees. 30,000 Reynolds per is a bit uh, weird, I think. I'll start with a million. So start at 0 degrees. You can see that the airflow, the red lines is basically the airflow that leaves the airfoil. So at 0 degrees, you can see that the airflow stays almost entirely attached. And as you increase the angle of attack, you see that the center of pressure shifts to the left, and also the what do you call the airflow is almost entirely attached as well. But at some point, notice if you remember at Reynolds number 1 million, we said the stall angle is basically like 14 degrees. So we are approaching almost 14 degrees now. As you approach like 14 degrees stall angle, you can see how the flow of the top surface separates. This is what I mentioned about the separation of flow. The separation means that the airflow is not deflected as much as earlier, and that is why we're losing lift actually during stall. So if you go even higher, you can see the separation get even more like drastic. So here it is almost entirely detached at 24 degrees. This is like extreme stall conditions. So yeah, that is that. You can also just click animate here to actually go through each angle. You can see the graph as well changing. Uh, if I hadn't mentioned it, the arrows are basically just a representation of this CP versus X curve. So you can speed it up or slow it down, the animation. So yeah, you can play around with this in your own time. So yeah, that is about the CP versus X distribution. CP, again, if you don't remember, the equation was P minus P naught by Q. So it is the difference between the pressure at the point and the surrounding pressure. If P minus P naught is positive, that means that the P at that point is higher than the surrounding pressure. P minus P naught is negative, means P at that point is lower than the surrounding pressure. So yeah. Pressure vector field, if you want to get, you can just tick the arrow here on the right side, pressure. Display. Under display, you can just click pressure. Uh, it's- so yeah, this one you can just get using just alternate between these, the polar view and the airfoil view. Top left here. Anything else? It should be no, CP is not in the polar view. CP will be shown in the what do you call the operating point view. Like I said, this is the only way you can get CP. So yeah. It might be grayed out because if you haven't selected any point, any operating point, if you're just here, then it'll be grayed out. If you just clicked on Clarkway airflow, it'll be grayed out. You have to specify any particular Reynolds number, and you also have to specify a particular angle under the Reynolds number for this to be visible, because it is only showing the active operating point. If you remember, I told you earlier how like the lower Reynolds numbers can get a bit janky. I can show you here, like this is the Reynolds number curve for 30,000. What do you call it? The Reynolds number equals 30,000. So you can see how like it's not really exactly as we expect. There's some like changes. There's some uh, unconverged points in between. That is what these like straight lines are, because it's just jumping from one point to the next. So it's not exactly ideal to use such a low Reynolds number. You should go into the millions. So yeah, that is airfoil analysis done. We will be going into wing analysis now. Any doubts so far? Anything else about airfoil analysis? Nothing else? Okay. Yeah, so let's go into wing analysis. You want to get into the 3D view section here at the top. So yeah, so for the wing analysis, this is actually plane analysis, but then we'll only be doing the main wing without the tail fins as well, without the tail or the elevator. So let's start it. How you start it is basically just go to module, wing and planes, and define a new plane. You can give it some name here, main one. Yeah, and we want to tick off the elevator and fin because we'll just be doing the main wing for now. Under main wing, make sure to go to define here, and you'll be brought into this view. Note for the 3D view, you can hold down your middle mouse button to rotate it, and you can drag it using the left click. Middle mouse button again to rotate it to the 3D view. So yeah, this is how we define a wing for the program. So what we can do is basically the way that XFLR5 is used to define wings is basically using sections. So if you see the red section here, that is what one is. The first row is basically this red section. If I click on the second row, you'll see that the red has shifted to the tips. So this is only two sections, the middle section and the end section, and XFLR5 basically linearly interpolates between those two. So you specify the sections and it basically connects those. So we'll start with the middle section. For both of those, go to the foil section and just click that. And you can set it to Clark by airfoil because that is the one we have analyzed. And the end as well, if you set it to Clark by airfoil, it should become solid. So this will be your wing. Yeah. So if you, I'll show you what each of these columns does. This is important because your assignment will be to make a wing basically, according to specified dimensions and run an analysis on. So yeah, the way we start is, so first of all, it is the y coordinate. This row is basically just the y coordinate. This column is the y coordinate. And for the central section, I'm giving it to be like at y is equal to 0. If I want, I can give some y is equal to 0.5. All these measurements are in meters, by the way. And what happens is like basically you only specified these two sections. So it'll join these and there'll be nothing in between. So ideally, this should stay at 0. There should be one section at the root of the airfoil, root of the wing, sorry. That is what y does. If I want to extend the wing, I'll just go into the y of the second one, and I'll set it to 2. Means it'll just, again, extend it to 2 meters. You can see the wingspan on the right here. Wingspan is 4 meters. That is because 2 and 2. So let's stay with 1 for now, 1 meter. Yeah, next is your chord. Chord is just the chord length of your section. So for 1, if I'm setting chord length as 1 meter, say, that means that it'll just extend to the 1 meter length. But this one is still at 0.1. That is why it looks kind of weird. I'll keep it at 0.2 or so for now. I think it was taking 0.1. And for the second section, if you change the chord, you can see how the wing changes as well. It's just changing the chord length essentially. But I'll just reset it to default. We'll run a simple analysis on a simple wing first. Next is the offset. This is basically the x-coordinate. If you haven't noticed, this is the x-axis, this is the y-axis. So the x-axis is basically the chord axis, and y-axis is like the span axis. So if you change offset, it is basically changing your x-coordinate. Like if I, for example, for section 1, that is the root, I change the offset to 1. That means that it basically goes all the way back there. If I change the offset to 0.5, it means it's shifted by 0.5 units. That's all that means. If I want the wing to be swept back further, I'll just go to the section 2 and I'll change offset to like 0.3. That will move the the ends further back and I'll get a swept back wing. But now I'll just keep it at 0.2 or something. So yeah. Then we have the dihedral angle. The dihedral angle is important. So you can go to your section 1 and try changing the dihedral angle. So for now I have 0. I'll see what happens if I put it at 30 or something. Basically, the dihedral angle is the angle that is formed with the y-axis by whatever surface is attached to the section that you're changing the dihedral angle for. So I'm changing it for the middle section now. So if I change it for the middle section, that means that everything that is attached to that middle section uh, will be at an angle of, so this angle is currently 30 degrees, is what dihedral equals 30 degrees means. This angle is also 30 degrees. Dihedral angle is used to provide something called as roll stability. That means that if you try to roll your airplane one direction, if your wings are shaped in like a V shape like this, the aircraft will on its own try to return to its original roll position, where to its stable like vertical horizontal position. So that is what this is used for. But we don't really need to study the mechanics of that. I don't think we have the time for that also. So that is mainly what dihedral is used for. But it's useful to have. So for the wing design, that is all that means. It's just a 30-degree angle between the surface and y-axis. Notice how the second section doesn't have a dihedral angle that you can specify. Even if you specify anything like 60 degrees, nothing, there's no change that happens to the aircraft. This is because like there's no surface that is attached further from the second section. That is why there's no change happening here. So you can set it to 0 for now. So I won't be using a dihedral for the initial analysis. Yeah, so next thing is twist. Twist is pretty self-explanatory, I think. It's literally just if I give it this is the middle section, by the way. I'm still on 1. So I'm giving the middle section a 10-degree twist. Means that the middle section by default will go like to a 10-degree angle, positive 10-degree angle of attack. If I give it some 30 degrees, it's probably more visible. So you can see how like the wing is now like twisted, whereas the ends of the wing are still at 0 degrees, and the just the middle section is at 30 degrees. So we won't really be using it too much, but it is good to have still. I won't be using twist for now. Notice if you remember, I said the dihedral angle of the ends like don't really matter. If you want it to matter, all you have to do is basically just click on click on the end one, just click insert after section 2. So you can add another section. And the next section is basically this end, the one's marked in red, if you can see. So I'll just extend this out to like 2 meters. And what you can see, note that if you like, you can tick these off. You can tick the surfaces off. You can see it a bit more clearly if you want. But I think surfaces is better. So yeah, so this is our last section. This is our third section that I've added. Now, if you change the dihedral angle of the second section, it has meaning. So if I change second section's dihedral angle to 30, you can see that now like the third section now makes an angle of 30 degrees. So this angle is 30 degrees is basically what that is. The third section's angle, this angle. So that is what you can do to make the dihedral angle a bit more meaningful for the end sections. You can add a different section. Notice how like if I change the dihedral of the root, this is a root, the first one, to 30 degrees also, this just means that what do you call, both the sections are at an angle of 30 degrees. So this full angle is 30 degrees. That is what that means. It's not what you would expect. Like it's not that the third section is at 30 degrees from the second section. It's that the third section is at 30 degrees from the y-axis. So if you want this third section to go at a further 30-degree angle to the what do you call, to the wing section, what you can do is just make the dihedral here for the second section 60. That means that you have your 30-degree dihedral here and your 60-degree dihedral for your third section. So now this is now 30 degrees with respect to the third section now has 30 degrees with respect to the second section. So yeah, that is what you'll be using. We won't be using a dihedral file. And third section is, you can just right click and delete sections. If you want to add sections, you can just click whichever one you want to add before or after, and just click insert after, insert after, insert after. We won't really be using it for the simple wing, at least. You will be using it for your assignments. There's a lot of sections and stuff involved there. So yeah, this is the thing that we'll form the initial analysis on. Yeah, so just the wingspan is 2 meters because y coordinate is 1, 2 meters. Let's just save this. and save again. Uh, you can also specify your inertia here, that is your masses under plane inertia. You can just go here and basically specify whatever it is you need. Mass, like point masses is basically you can specify here. And for the mass of the wing, you can go to main wing here and you can add the wing mass here and any additional point masses on the wing here. We won't really be dealing too much with this, but this is what I mentioned earlier about CM versus alpha graph being more significant with plane analysis, because here we are able to specify a center of gravity about which the moment is calculated. So what we do to find the aerodynamic center experimentally or like using the software is that you use trial and error and you basically set point masses such that point masses at different chord lengths such that basically you'd keep doing it until your analysis gives you a CM versus alpha graph that is almost constant. And then you can say that that point that is fixed as your center of gravity will now be your aerodynamic center. So that is how we can find center of what do you call aerodynamic center using center of gravity and masses here. We won't really be doing that. I don't think we have the time for it. We'll just be doing the basic analysis. So you don't really have to worry about plane inertia. Your assignment also won't really be including that. So yeah, so this is your plane or your wing rather. You can take off elevator and fin, like I said, you don't need it. Just click save. Again, you can toggle on or off surfaces here on the right side. Uh, yeah, so you have defined your plane, and I think I've explained all the ways to what do you call to give the angles and lengths and stuff. So yeah, we will be doing the analysis now. Before that, like any doubts in the section?
Yes, by the way, I'll be sending the attendance to link like shortly. In the session channel, go check that.
Someone has asked here about like reversing the airfoil. What you can do is basically go to XFLR5, right click, current plane, edit, and under the main wing define, instead of giving y is equal to 1, if you were to say give y is equal to -1, what that does is basically it inverts your airfoil. But then again, it's just the same analysis, but just entirely reversed. So it inverts your ends as well as your chord. I mean, ends as well as your root of the airfoil, of the wing. So this is how you can reverse the airfoil if you ever want to do that. You can just give y as -1 instead of 1. Let's give y as equal. So we'll just be doing a normal wing here. Save, save. Nothing else about this. Okay, we'll do the analysis now. For the analysis of the wing, just go under analysis, define an analysis. And again, here also we'll be doing the fixed speed analysis, the type 1 analysis. The earlier analysis that we saw, fixed angle of attack and fixed lift and stuff is still available here, but mainly we're interested in the fixed speed. So this is the wing design window. This is what I mentioned earlier. You can see in this window the Reynolds numbers that you will be having at your tip and root here. Root is basically your middle, by the way, and your tip is the edge of your wing, or the ends of your wing. These are different because, as we said, Reynolds number is defined as rho v L by mu, and L is basically the chord length. And chord lengths are different at the tip and the wing here, tip and the root here. The chord lengths are different. That is why these quantities are different. So yeah, earlier, like I said, we ran the batch analysis for the Clark Y airfoil under this. And for that, the Reynolds numbers that we used were like 30,000, 40,000, 60,000, 70,000, 80,000, all the way up to like 8 million. So here I've covered almost like all the like important, like a relatively uniform intervals I've covered the Reynolds numbers. So like I said, these Reynolds numbers have to include, have to cover a good range of what you're expecting to see. Hello, can you hear me? Okay, I think I got disconnected for a second there. Around like where did I finish? Did you see this window, like the analysis of the plane? Okay, I'll just repeat that section. The way that you can start the wing analysis is just go under analysis, define an analysis. Um, and yeah, you can just, the earlier types of analysis are still available for the fixed lift, fixed AOA, but we are interested in the fixed speed analysis. Like I said earlier, like the Reynolds numbers for the tip and the root are provided here according to your specified quantities. Here I've given V infinity, that is the free stream velocity we mentioned earlier, V basically in the equations. It is this same V. This V is the free stream velocity. That is V infinity here. So say I'm giving it 10 meter per second. You can see at 10 meter per second airspeed, see the Reynolds numbers are like for the tip is 73,000 and for the root is 120,000. The Reynolds numbers are different for the tip and the root because the chord lengths are different, by the way. Reynolds number has this like quantity that is rho v L by mu. So L is chord length here. That is why the tip and root have different Reynolds numbers. So yeah, again, V is also present in the Reynolds number. So we can change V infinity to be, say, 50 meters per second. And you can see the Reynolds numbers here change as well. So that is how you can change the target Reynolds numbers that you're using. If your chord length is too small, make your velocity higher so that you can get the Reynolds number that you want. Um, in any case, like for identical Reynolds numbers, even if your chord length is smaller, you can increase the velocity to get the same Reynolds number. And at the same Reynolds number, the behavior of the wing will be almost exactly the same. So that is one interesting point. So what you have to make sure is that these Reynolds numbers that you have mentioned, that are mentioned here for your wing analysis, have to be, let me just save this first. So 15 meters per second. And under the analysis tab here, you'll have to mark LLT. This is called the lifting line theory, I believe. It's basically just one theoretical way of analyzing the wing. This has given me the most accurate results, I think. So I would advise sticking with this, but 3D panels is also interesting to see. Um, so LLT is what you'll be doing. You can go to the LLT, just mark LLT. Everything else you can just leave as it is. It's almost like just my settings are also default, I think. You can just save this. So like I was saying, like the Reynolds numbers that were stated during your analysis, here I believe it was like some 300,000 or something, 300,000 and some 600,000. If you remember the batch analysis we did earlier, I've included like almost a good range of Reynolds numbers. Like I've got 300,000, I've got 500, I've got 750,000. This means that like my wing analysis Reynolds numbers that I used for like some 300,000 to some 500,000, I believe it was, for the tip and the root, then those you have to make sure that those Reynolds numbers have to be included in your batch analysis here. Because if you haven't included those Reynolds numbers, like not exactly, but then it should, like a closer Reynolds numbers at least should be included. So I had some 315,000, but then I have already given like 300,000 here. So something close should be included here. It should be like covering a good range of Reynolds numbers. So that, because like I said, what the program does is it uses this pre-calculated data from the batch analysis for your wing analysis. So you have to make sure that a good range of, for those Reynolds numbers for your wing should be present here in the batch analysis. Like almost a close Reynolds number at least should be present here to avoid any errors. So yeah, wing design again. Uh, yeah, so we have defined the analysis. That is this one, T1, 50 meter per second, LLT. LLT is the method of analysis. It's, I think, the most accurate for XFLR5. So I would advise sticking with that. So yeah, once you've defined that, on the right side, you can see the star again, like with the alpha. So you can specify your angles of attack. I'll be doing an analysis from -5 to 30 degrees with an increment. This is the increment again for 0.5 degrees. You should probably take this one as well. I think it helps. Initialize LLT, I guess, and both of those just should take it. And once you defined your start and end angles and your increment, you can just click analyze. Again, like earlier, you'll get a window, but here you'll see a lot more unconverged uh, messages. That is basically like we see that from alpha equals -5 to alpha equals around like 14 degrees, there is convergence. If you remember, the Clark airfoil stalls at around 14 degrees. After stall, like LLT method that we see is it's not really great at calculating the values after stall. That is why these are all going unconverged. It's not really like if you want, I think this should be enough for like most analysis, but yeah, if you want to like get a bit more accurate, you can go to the different analysis methods. But then that is all that they also have their own like quirks and their own issues. So I've seen that the LLT is the most stable and the most accurate. So we'll be doing the LLT. It's fine. You don't really need too much information beyond the stall. So these are all unconverged. That's fine. Everything else is converged. So below 14 degrees, everything is converged after some n iterations, 40 iterations. So we'll just close this. If you get any errors, the error messages will be mentioned here. If your Reynolds numbers in your wing section are not in your batch analysis range, then you'll get some error like some points are not included in the flight envelope. That is when you have to go back and check your batch analysis. I've mentioned that in the PPT as well. I'll be uploading PPT. So you can close this once you're done. And this again you can just click through these to show your different angles. So yeah, let's start at 0 degrees. On the right side, under display, you can click all of these different quantities. So if you click on lift, you can see the visualization of lift. If you remember, like at the start of the session, I told you to go to like view and 3D scales. I think 3D scales shows up when you have done your first wing analysis. That's why I wasn't showing it earlier. So 3D scales will show up once you've done this, and make sure to set your 3D scales to like something. 0.1 should be fine for most. I'm using 0.1 here. So what this does is basically it's just defining the length of these vector arrows. If I these were set to 0 by default for me. So if what happens if you set to 0 is the arrows just don't show up. You'll just get the line. So that's why you have to set it to something like non-zero. So I'm giving 0.1 here. Again, that's under view, 3D scales. So yeah, you can go under display here and tick whatever you want to show. So here I'm showing the green arrows are lift here. So I can tick it on and off. This is lift. So this is the lift distribution along the wing. What you can see is that the lift is maximum closer to the center and it's decreasing towards the end. This is due to something called as wingtip vortices, like you must have done in session one, I think. These wingtip vortices basically reduce the efficiency of the wing closer to the wingtips because obviously the wingtip vortices occur at the wingtips and the efficiency closer to the tips is reduced. And since that efficiency is reduced, the lift it's generating is reduced. That is why you see this elliptical distribution. It looks close to an ellipse. So yeah, that is about the lift. And this is at 0 degrees. If you just go higher and higher, you can see the lift increasing. The red arrows, I'll explain what it is in a second. The what do you call the lift distribution, you can see it becoming a bit more pronounced as well at a higher angle. So yeah, you can click the moment arrow here to see the pitching moment. Uh, Pitching moment visualization is a bit weird. The arrow here essentially is like the yaw moment. Arrow here is basically like your roll moment. And those ones are 0 because our airfoil is kind of being asymmetric here. So it's not really tilting to the side or rolling. So this arrow set here, I'll turn off downwash. This arrow set here is basically your moment arrow. This means that it is trying to rotate the airplane nose down. This doesn't mean that the moment is anti-clockwise. This means that the moment is clockwise. So that is, it is trying to rotate the aircraft down or the nose down. So this is what we said, pitch down or nose down moment. It's kind of a weird visualization, but yeah, it means that it is trying to rotate it clockwise from this side. So yeah, this is the lift distribution. Again, you can note how like this is the overall like averaged position. This is the overall arrow, the lift arrow, and this is like the total lift representation. This one in the middle. I think this is like the average position of all of these arrows as well on the x direction. So that is why it's a bit further back than you would expect. These are the individual points at which these are acting are the centers of pressures of each of those like wing sections, which moves further and further back because your airfoil sections are moving further and further. So yeah, that is it about the lift moment I've shown you. Next is downwash. Like I said, the wingtip vortices act like at a very high intensity towards the wingtips. So that is what this is the forward view, by the way. You can switch between views on bottom right, like section here. You can just click these to see the different views. So I'm just going to be using the forward view. This is looking straight ahead. So the wingtip vortices basically act at a very high intensity towards the wingtips. And this means that since this vorticization happens, the what do you call the airflow is basically in an so I'm looking at the right what do you call my right wingtip here. So here the vortex will be like in a counterclockwise direction. This means that because the vortex forms because the pressure on the lower surface of the wing is higher than the pressure on the upper surface of the wing. The bottom is high pressure, top is low pressure. So the air tries to move from the high pressure to the low pressure, thus forming like a counterclockwise vortex here from the bottom to the top. So what happens is that since that vortex is formed, the air near the wingtip, basically gains a downward velocity due to that vortex. The vortex is basically having downward velocity inside of the wing section and upward velocity outside because it's counterclockwise. So downward here and upward towards the end section. So that is what is giving this like downward velocity towards towards the air at the end. So that downward velocity is what this downwash arrow is. This red arrow is basically representing like how far the air is going down, how far downwards the air is deflected at any particular air section. Like I said, airfoils basically deflect the air that is coming in one direction to a direction that is further down from them to generate an upward reaction force lift. So here, due to that wingtip vortex, we see that the what do you call the airflow is deflected much further down towards the wingtips as compared to the center and everywhere else. This is why, if you remember, when we defined the like airfoil lift coefficients, we defined them to be over like infinite span lengths, basically. So so as to avoid these issues, and we want like a uniform distribution. So that is it about downwashes. Then there's something called induced drag. So induced drag, I think you did in your first session, but it's not as important. So I'll just be like mentioning it in case. Uh, I'll just be mentioning it quickly. Like I said, the wingtip vortices basically reduce the efficiency of the wing towards the wingtips. And reducing the efficiency means that it basically takes whatever, like the lift component is basically angled backwards. So what happens is that this same aerodynamic force is acting almost entirely here, but then that aerodynamic force is angled a bit towards the back due to the wingtip vortex. And that means that the particular component of that angled backward lift is getting resolved towards the drag direction. And only a little bit of that is getting resolved to the lift direction. That is why this lift arrow is smaller. So that resolved drag direct that what do you call the net aerodynamic force that is resolved in the drag direction due to this shifted lift is called as induced drag. So it is higher towards the ends here simply because the wingtip vortices act at maximum strength towards the wingtips, and that is causing this shift of the lifting arrow further backwards to a super high extent. That is basically what this is showing, the induced drag. So it's generating a high amount of induced drag towards the wingtips. This spike, I think it's a bit of a mistake actually. It shouldn't really be showing a super high like induced drag towards the root of the wing. I think it's a mistake of the software, but I'm not really sure. It should mainly just be having a high induced drag towards the wingtips. That is about induced drag. And that is mainly it. Like that is mainly all the quantities you're seeing. Again, you can go like on the top left, you can select polar view here. This is your polar view. We can see the same graphs that we did for your airfoil analysis before as well. Here also you can see the CL is almost like following a linear trend with alpha. This is a CL versus alpha graph. CL is following almost a linear trend with alpha. Your coefficient of moment versus alpha is, again, this is what I mentioned. Here we haven't really mentioned the center of gravity. We haven't given any inertia or point masses for the plane. So XFLR5 takes the default reference point as the leading edge. So it is taking the moment about the leading edge. This means that if you take the leading edge as a reference point, the moment is always negative and it is decreasing with alpha, or like increasing in the negative direction with alpha. So this means that it is a stable flight because, like I said, we want the moment to be negative as you go to a higher angle because you don't want it to ever stall. You want it to stop itself before it stalls. So this means that if you let the airplane like basically move freely at an angle of 10 degrees, it will always try to come back. It will always try to pitch the nose down and reduce the angle instead of trying to stall, instead of trying to increase the angle and eventually ending up stalling. So this is a stable aircraft in the pitch direction at the very least. So that is the CM versus alpha curve. If you do want to, what do you call, say, find the CM versus alpha curve with the moment taken about a different reference point, what you can do is you can specify, go to plane, edit, plane inertia. Under main wing, you can add some point masses. I believe the chord length for the route was like 0.18 meters. So if I'm going to give like 0.25% of the chord, I'm trying to make the center of gravity to the aerodynamic center, basically, so that I can take my moment about the reference point, aerodynamic center. So I can just give like a point mass of maybe 1 kilogram. This is the mass, if you can't see. At a distance of x equals 0.18 by 4, which is like 0.045. I mean, sometimes it tends to be different from what you expect. It's not always at 0.25 C. That is simply because like our wing is not uniform. Our wing has like two sections that are entirely different. If it were like a rectangular wing, it might be like giving at exactly 0.045. But I think you might have to angle it a bit further back here. 6.06. And you can just save that, and that'll give the wing some inertia. Uh, you can click here to see the masses under display again. So like if you modify your plane in between an analysis, what happens is like your initial analysis results get deleted because it's no longer valid. So I'll just define the analysis quickly again. Again, if we go to the polar view, we see that it is still kind of CM versus everything else is staying almost the same. All the other curves are not really affected that much by adding mass or center of mass. But like CM versus alpha is affected because that is your point. The center of gravity is the point about which you're taking your moment. So here it is still not far back enough, I think. I'd have to angle it a bit further back. This is a trial and error I mentioned earlier. You're trying to basically move it until the CM versus alpha graph is basically getting a a constant value for a different alpha. Second. So what I did was basically I just moved the point mass a bit further back again. So as to change the center of gravity to be further back. still decreasing. It is supposed to change. Just trying a bit of an exaggerated thing just to show that it does change. It does change. You see the CM versus alpha graph changes to basically like an increasing one here because I've made my center of mass so far back that like it basically everything looks like a nose up moment to this reference point. So basically, you just keep doing trial and error and move the center of mass back further and further back until you get a graph where CM versus alpha is a constant. It's a bit, I'm not sure. I'll try one more time, but if it doesn't work, it's not really important. I'm just showing you the method that like you will use to find this. It's not really like it's not part of the assignment or anything like that. Yeah, I think this is almost good. So this is a CM versus alpha curve with your center of mass that is set to almost like 0.12, I think, 0.12 meters from the origin is the center of gravity of the mass that I set. So as you change the center of gravity, you're changing the reference basically. And you can see how CM versus alpha is almost a constant for a good range of alpha. So that you can say close to 0.12 meters from the origin will be your aerodynamic center. So that is just a cool thing. So you can also notice that all the other graphs basically stay like unchanged with the center of mass because the mass doesn't really affect the CL and stuff too much. So yeah, this is now like you can see the same graphs that we did earlier, CL versus CD, CL versus alpha, almost the like same linear trend we're seeing for CL versus alpha. Then CM versus alpha, like we said, we're basically taking it about the aerodynamic center, which we found by trial and error. And that is why it's almost a constant with alpha. You can see it is almost a constant. It is still changing at a higher angle. So yeah, that is your CM versus alpha. CL by CD, again, like efficiency curve. It's almost like maximum at an angle of 2 degree or less, slightly less than 2 degrees. Around 1.5 degrees, you're getting CL by CD, highest efficiency. So it is basically the same curves that we saw in airfoil, but with accounting for spanwise effects and also changing chords and stuff like that. This, I'm not really sure why it's separate. It's a root of CL cube by CD squared. I'm not sure like why you use this in particular, but it's basically like similar to the efficiency curve itself. So yeah, that's almost everything done, I think. Um, yeah, the second attendance form has been shared, right? Any other doubts about wing analysis? Because I think this is almost it. We're almost done. So yeah, that's it. These are all our main graphs. And also there are some graphs about the induced angle and the effective angle and stuff. You can see it on the OP point view here, the top left. This is not really that important, I guess, but then It's simply just like a induced angle is just a measure of the downwash. So the higher the induced angle or higher the magnitude of the induced angle, that means the higher the downwash. This is the same thing that we saw with the downwash arrows being longer towards the edge. So that is mainly it about this. This is basically the effective angle. And we see the effective angle of attack decreases towards the edge simply because the effective angle is just the actual angle of attack minus the induced angle of attack. Total angle is basically effective angle. Since the induced angle is decreasing, you're getting a lower and lower total angle towards the edge. This is basically just a representation of the downwash as well. Nothing really too important. This is again the lift distribution that we saw. Like we see, like I told you about an elliptical distribution, right? So it is highest at the center and decreasing towards the edge due to the downwash effects. That is basically just this local lift versus X graph. Uh, this is not really that important for you. I think it's not that important because we're seeing the same downwash effects here. So that is it. I think that's everything. And there is some stuff about the assignment. I'll be uploading assignment on Teams after the session. So your assignment will just be to make the same wing session, the wing section from what you did in session two. Session two, I think you had Fusion 360, where Haritosh made like an RC plane. So he has given me the dimensions for that wing, and you'll be making this wing, mirroring this wing using XFLR5 wing design. And all the measurements are given here. It should be pretty simple. You'll be using a lot of the sections and stuff to make the winglet. Basically, you can use like 3, 4 sections to make it a bit smoother because, like we saw, like if you're using one section, the return will be a bit sharp. So it's fine even that way. But yeah, the angles and everything are marked here as well. If you want a bit smoother, you can add more sections. You'll be like doing a type 1 analysis at a speed of 100 meter per second. And you will be like, finally submitting the coefficient of lift and coefficient of drag at alpha equals 10 degrees. So yeah, I've given the airfoil date files and stuff. The slide is about, the Reynolds number being included in the batch analysis section. That's it. Like when we were starting the recording, I forgot to like start the recording with the PPT section. So I'll just scroll through this a bit just to, almost all the information is in the slides. Just to include it in the recording, I'm just going through this. Everything else I think I've covered in the recording. So that's it, guys. Thank you. If you've marked the attendance Safari 5 tutorial, I'll be sharing the slides if you want. Is there anything else you need? The video also will be shared, I think, on YouTube. If there's nothing else, and if you fill the attendance form, you can leave. Both the attendance forms.